I'm bored. I'm going to do something. We are going to do a ray diagram. Typically done by second semester intro physics students in both the Cal-based and the algebra-based physics. High school level physics from time to time. There's going to be a lot of stuff coming out. The first thing we're going to do is we are going to write the problem. A convex lens, we're going to go simple. Convex lens with a focal length of 20 centimeters has an object (30 centimeters to the left. Where is the image? And describe it. Draw a three-ray diagram for it. Okay. So, step one, do the math. Do the math. Do the math. A lot of people just want to start drawing. Don't do that. You first have to use the almighty equation. 1 over focal length is 1 over object distance plus 1 over image distance. Solve for I. 1 over I, 1 over F, minus 1 over O, which leaves us with image distance is basically inverse focal, inverse object, and then you invert that. So to get where the image is, plug and shut. Focal length is 20. Object distance is 30. You invert it. So you get your trusty calculator. 20 inverted minus 30 inverted. Invert that sucker and you get 60. Next, get magnification. M is negative I over O. Both of these equations are the same for concave, convex, lens, mirror, doesn't matter. Image distance, 60. Object distance, 30, which is negative 2. Now, here are the things. If the image is greater than 0, which is what it is, then the image is real. If the image is greater than 0 and a lens, it's to the right. So we have two of these things. There'll be a video later where I just basically just crank out all these meanings. But as for right now, image greater than 0, it's real. Image greater than 0 and it's a lens, it's to the right. Since the magnification magnitude is greater than 1, it's enlarged. And since the magnification is less than 0, it is inverted. Which means that if you have an arrow like that as the object, which is the standard, that's the standard object that they use for all the images, you invert it and make it larger, which means it will look something like that. So the 4 descriptors for this: real, right, enlarged, inverted. The reason why I do this first is to know exactly where that image is. Now let's draw this bugger. the key is to not screw up the very start. You start with the optic axis or optical axis. Draw that out. Now, I don't draw the specific image of a convex lens or a concave lens. I just draw a vertical line. It complicates things and introduces way too much trouble for what needs to be done. So you look at the largest number. Focal length is 20, object is 30, image is 60. That's the biggest guy. The image is to the right of the lens, which means the first thing you really do is place and label where the object is furthest away from the lens, which means that if the object is 30 centimeters to the left, the image is 60 centimeters to the right. To keep everything in scale, the lens wall has to be a little bit left of center. So this is 20, that's the middle. So it's going to be over here a little bit. I need to pick a scale. Let's just say that 2 centimeters on the page is equal to hold on, I had a perfect idea. 5 centimeters in the lab. So let's see, that would make it there. All right, so 60 centimeters is in fact 12 centimeters on the page, which leaves that here. That is where the lens wall will be. The object is 30 centimeters, which means this is, let's see, well, actually, I got it all, a 2.5. It's 2.5 centimeters that I picked for some odd reason. Now, that's 30 to the right, 20 to the left. 20 divided by 2.5 gives me 8. Okay, it's not that bad. This is the only part where it's a little bit kind of like an art to all of this. It's just picking out the numbers right, so it all kind of fits. All right, so that is there. Focal length is 20. Or actually, I already screwed it up. I'm going to edit and post. So let's make this simple. I need to fix stuff. The thing about physics is making happy errors and always bring a little bit of white out. Bring a lot of white out. A lot of white out. All right. So I need roughly, let's keep it simple. 1 centimeter on the page. I was trying to get cute. 1 centimeter, because I don't have enough room for any of this. So 1 centimeter on the page is 5 centimeters in the lab, which means that our true location of image, 1, 2, 3, 4, 5, 6, just divide everything by 5, which means we get rid of that. And actually, I'm going to leave all the edit or the bad parts in, because a lot of times people think that we just do this stuff and we automatically know. But by seeing the mistakes, you can actually see how you recognize and recover. You recognize the problem, you recover from it. And I think that's something that professors don't normally teach. So over here, that's 6 centimeters to the right is the image. That means the focal length is actually 4 centimeters to the right. We're dealing with a convex lens, which means that the focal point is to the right. So you're going to have the convex lens, you're going to have the object over here, you have the image over here, you have the focal point, and then on the left side, we have what I call the antifocal point. It's a reference point, and it's on the opposite side of the regular focal point. And what these focal points do, just to kind of show, I'm actually going to draw it, is that the focal point is where the light either refracts to or refracts from when it comes from a mirror. So you get this. That bends a little bit. I'm taking some creative freedoms with this. Oh, this is going to be horrible. But the grand scheme of things, it takes this parallel light and focuses it on the focal point. Now we've got focal point, antifocal point, image. Let's get our object. That is, wait, did I even screw this up again? No, I did fine. Oh, I really screwed it up. Here we go again. So object is 30, which means that's 6. There we go. I know everybody at home is screaming if you've made it this far. Which means that the image, which is 60, is in fact 12 centimeters away. So let's see, do we have enough room? Yes. Okay. And so the image is there. All right. So divide by 5 for all of this. 60 divided by 5 is 12. That's 12. 20 divided by 5 is 4. There's 4. There's 4. Object is 30. 30 divided by 5 is 6. That's 6. Everything is placed properly. Now for the image drawing and object drawing. It's a double size, which means you pick a reasonable number where you know you can draw it on the other side. So if this is 3 up, 3 centimeters up, the image has to be 6 down because it's negative magnification. And it's 2, which means you go 6. And this is it. Now, there are 3 rays. Time to get the colored pens. The 3 rays are through middle, starts parallel, finishes parallel. Now, I went through all the trouble, and everybody has to go through all the trouble, in setting this up. Makes things a lot easier if you draw your image and object and everything is placed perfectly. The first ray, the ray that goes through the lens, is unaffected by the lens. It doesn't bend at all. It's because it's passing through the physical center. When I taught for 7 years in general physics, a lot of time, I mean, there is a reason why, but since I don't have calculus, I don't normally do the derivations for that. All right, the next one, so first one goes through, ends up right at the image, right where it's supposed to be. Now, I was worried up until this point that I kind of screwed things up with the placement, but everything is fine now. The second ray starts parallel and remember what we said before, that the parallel light goes through the focal point. So you line up where it interacts with the wall, the focal point, and the image. And voila, lines up again. Now the third ray is a little bit sneaky, but this is how I kind of deal with it. The third ray finishes parallel. That's the key part. So what I do is I draw that ray first. Draw it up like that. And what you notice is when you line everything up, the object, the antifocal point, and the intersection point that becomes parallel for the ray all line up together. The convex lens that produces a real image is probably the easiest of the types, and so I just wanted to get started with doing this. Eventually there'll be others where I'll go through all the permutations. But this illustrates the general idea. I think it shows some interesting techniques about how to, I don't know. A lot of people just say, oh, it's in the book. Well, I think it's better that the book is in my skull and I'm letting it out for you to see. And I'm showing you all the pitfalls and warn about that. But that's it. If you like what you see, hit the like button. More stuff will be coming out tomorrow. And the big news is tomorrow I go insane. And tomorrow I start an 18-day run where I cover all of intro physics, general physics, so this is just the algebra based, first and second semester. And I'm going to cover it in 18 days. I've done summer school where I've taught a whole semester in 28 days, and that was rough. Now I'm going to double up with doing 2 semesters in less time. My advantage, I don't have to give tests and I don't have to grade. And that's enough. What else do I need to say? I love writing tests. I don't like grading them. That's why I ended up getting a lot of grad students to be my graders. So if you're interested in getting private tutoring, let me know. I do intro physics. business calculus, calculus. If you know anybody who needs help, I'm there for you. As you can tell, I speak well, I enunciate, and I really enjoy this. There's some other things. Statistics, I do that. But I really enjoy the introductory stuff. Love it. Like intro, econ, micro, that kind of stuff. And that's it. We'll do more. Thank you for watching. Bye. How do I turn this off? I don't know. Oh, stop recording. That would help.